How you do? How you do? Can you howl? Can you say, oh, woo, ow, ow, ow? Can you do it? Ow, 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 Good girl. Okay, go, go. All right. Hello, those of you who are here already. I'm going to wait just a little bit longer for more people to join. There's 12 people watching right now. And I'm going to wait until there's a little bit closer to the full class size. Good morning, everyone. I'm going to wait until there's maybe 17 people watching concurrently. This is a pretty small class. I think it only has 21 people in it. I guess all the IB students decided to take bio or something. If you're just joining us, we're waiting for 17 concurrent viewers, and then I will begin the lesson. I know, right? Big mistake taking bio. That's how I felt about it. Actually, I took AP Bio when I was in high school, and I actually enjoyed it, but I just enjoyed AP Physics so much more. And we didn't have IB. I don't know if I would have done IB. You know, if I were a student, I would not have done IB simply because I'm not a strong English student. So you know how to do IB, you need that breadth. Oh yeah, they could have done sports and exercise. SEHS. All right, so I'm going to go ahead and get started, and hopefully the rest of the class will join in. So a couple of announcements. So your daily quizzes or assignments or whatever you want to call them, they are always due the Friday of the following week. So last week we met on Thursday, and I gave you a daily assignment. That quiz will be due tomorrow, okay? And similarly, I will see you guys twice this week, so we'll have, or actually, no, I'm just seeing you today this week. So the quiz that I assigned today will be due next Friday, okay? So you always have until the Friday of the following week to complete the quiz, all right? And I remind you that you can try the quiz as many times as is necessary for you to get the score that you want. All the quizzes are worth 10 points. Even if there's not 10 problems, I will scale it to 10 points. I want to remind you, if you haven't already, to submit your daily attendance. And after I'm done with this lesson, we will meet over in the Zoom room. Okay? So, I'm going to go ahead and switch to my document camera and we can get started. So before I do my lesson today, I just want to do a little digression about slope. Hang on, I gotta rearrange my desk here. Got too much stuff. Okay. Oh, there was a question. Do we need to do daily attendance on Wednesdays? No. No, because we don't have class Wednesday. It's only the days that we have class. And I hope you didn't wake up at 9 o'clock to submit the attendance. All right, so let's do a little digression about slope in mathematics. Okay, so the formula for slope is y2 minus y1 over x2 minus x1. Okay, that's slope in math. And these are the coordinates of 2 points. So you have a, maybe you have a point x1 comma y1, and then you have another point on the line that is x2 comma y2. All right, and then that's the slope. So let's think about this in another way. We could think about it as you start here and you end here. All right, so using the language of physics, we would say we have an initial point and a final point. Okay, so I could rewrite that as y final minus y initial over x final minus x initial. All right. Then we can use more physics terminology, where actually this isn't really physics terminology, but we can use more lingo to realize that final minus initial is just delta. Okay, so we have delta y over delta x. Okay, and then we're going to go one step further, because not all graphs have y on the vertical axis and x on the horizontal axis. Not all graphs have that. Okay, and we'll see that in just a moment. So I'm not going to call these the y-axis and the x-axis. I'm going to call it the vertical axis and the horizontal axis. So this isn't really y necessarily. This is just whatever is on the vertical axis. So I'm going to write it as change in vertical divided by change in horizontal. Okay? And this is slope. Okay? Slope is change in the vertical divided by change in the horizontal. All right? So that's kind of a nice way to think about what slope is. Okay, so let's have a little example. This is an example from when I woke up this morning. Okay, I woke up this morning and I was really groggy, and I was just kind of wandering around aimlessly. Okay, so I'm going to represent my motion by a number line. So I'm measuring x in meters. Okay. And I started off at the origin, which would be where I slept. And I then walked to position 7 meters. and that took me 4 seconds. And then I got to position 7 meters, and I forgot what I was doing. I was really groggy, so I just kind of stood there and I scratched my head and, picked some sleep out of my eyes. And so I was just sitting there. I wasn't moving at all for 3 seconds. And then I remembered that, oh yeah, the thing that I wanted to get, which was my coffee mug. By the way, I have the perfect coffee mug. It has a black Boston Terrier on one side and a brown on the other. I went to go get my coffee mug, which was all the way over on the other side of the origin at x equals minus 3 meters, and that took me 2 seconds. Okay? So this is a description of motion. So what I want to do is I want to represent this as a graph, okay? And so we're going to use we're going to draw what's called a position time graph, okay? Which is also called an XT graph. An XT graph, okay? So an XT graph has it has position in meters. So what we want to do when we're labeling the axes is we want to put the symbol for the variable and then in parentheses the units of that variable. And then we have time on the horizontal axis measured in seconds. So we want to sort of translate this story into a position time graph, okay? So I started at time 0, I started at the origin, okay, at x equals 0. Then I moved to position 7. So maybe here is position 7 meters, okay? And I did that in 4 seconds. So when I got to time 4, I was at position 7, okay? So I'm going to draw the line connecting those. Okay. All right. And then for 3 seconds, I just stayed put. Okay. So my position number was remaining at 7. Okay. For 3 additional seconds. So what was the total time elapsed? Remember, this is tracking the total time elapsed. 4 seconds and then 3 seconds, so I'm going to go all the way to 7 seconds. And I stayed put at this location, so my position number was not changing. Okay. And then I traveled to x equals minus 3. So this is x equals 0. So x equals minus 3 is maybe right there. And that took 2 seconds. So 2 seconds beyond the 7 seconds. So that would take me to perhaps it'd take me to 9 seconds. And I ended up at position -3. So I go from here to here, like that. So this is a graph representing this story. Okay? It's built up out of 3 line segments. So what I would like to do is I would like to go ahead and talk about what does the slope mean in this case. Okay, slope is change in vertical over change in horizontal. Now, what is the vertical variable in this case? The vertical variable in this case is x, the position. Okay. So I have delta x. The horizontal variable in this case is time. So slope of this graph is change in position over change in time, which is velocity. Okay? So that is the meaning of the slope of a position time graph. Okay? That is the meaning of the slope of a position time graph. Okay? Now you might say, well, gee, Mr. P, this graph is made up out of 3 line segments. Okay? So when you say slope, what do you mean? I mean the slope of one of the particular line segments. Okay? So there's a concept called the instantaneous velocity, which is the velocity at a particular moment. Okay? So what if I said, what is the instantaneous velocity at 2 seconds? Well, 2 seconds would be right here. This is 2 seconds. And so I would see that 2 seconds, at time 2, I was on this line segment. So I would want the slope of that line segment. Okay? If I said, what is the instantaneous velocity? Like, for example, what if I wanted the instantaneous velocity at 8 seconds? Okay? 8 seconds into this journey here would be right there, which is this line segment. So I'm asking, what is the slope of that line segment? So let's go ahead and calculate it. It goes from, for this line segment, it starts out at position 7, and it ends at position -3. So who can tell me the displacement if you go from 7 to -3? I'll wait a second while you guys type that in to the live chat. And the time elapsed, well, this line segment exists from 7 seconds to 9 seconds. That's 2 seconds elapsed. And I'm waiting for the, very good, yeah, it's -10. To go from 7 to -3 is -10. Make sure you include the sign to indicate the direction. Okay? So this would be -5 meters per second is the instantaneous velocity. All right? The minus sign indicating the direction is in the negative direction or the leftward direction. Okay? Boom. So now let's talk about how is acceleration represented in a position time graph. Okay. How is acceleration represented in this graph? Well, acceleration is defined as the rate of change of velocity, change in velocity or change in time. Velocity, we learned, was the slope. Okay. So this is actually change in slope over change in time. So acceleration, what does that mean if you have a graph where the slope is changing? The slope is going from maybe here to here to here to here to here, something like that. So acceleration is basically the bendiness of the position time graph. Okay. So that is acceleration. Acceleration is the bendiness of a position time graph. Okay. So let's draw a position time graph that represents acceleration. So it might look like this, like a parabola. Okay? Or it could look like this, anything that is not a straight line is going to be an accelerating graph. Okay? So that is how acceleration is represented. You could have a graph that starts out bendy and then it becomes linear. So that's a graph where you're accelerating for a little bit and then you're going at a constant velocity. So that's also a possibility. All right. So what do you need to know about position time graphs? You need to know that the slope is the velocity, and you need to know if it is bendy, that is the acceleration. Okay. I will ask you to actually calculate the velocity, but this is not a calculus-based class, so I'm not going to ask you to calculate the bendiness. I will just ask you questions like, is it accelerating at this time? So for example, if this is my position time graph, and maybe this is 3 seconds, and maybe this is 1 second. If I asked you, is it accelerating at 1 second? You would say yes, because at 1 second, the graph is bendy. Okay? Is it accelerating at 3 seconds? No, because at 3 seconds, you're on this straight line segment. So that's no bendiness, no acceleration. Okay? Another kind of graph that we could draw is a velocity time graph. Also known as a VT graph. Okay? A VT graph. So what is a VT graph going to look like? Okay? Let's go ahead and draw the velocity time graph corresponding to this position time graph. Okay? So when I draw a velocity time graph, that means that it has velocity in meters per second on the vertical axis, and it has time in seconds on the horizontal axis. Okay? So if I look at this, what is the slope, what is the velocity of this first line segment? Okay. The velocity would be a rise of 7 and a run of 4 seconds, which would be, that would be what, 1.75 meters per second, plus 1.75 meters per second. Okay, so that is the slope of this part. What is the slope of that part? It is 0 because it is flat, and then the slope of this part was -5. Okay, so let's see what that looks like. So notice how this entire line segment has the same slope. So everywhere from 0 to 4 seconds, we have a velocity of 1.75 meters per second. So here at 1.75, just stay steady at 1.75 until we get to time 4 seconds. Okay? Now what happens at time 4 seconds? The velocity transitions to 0 meters per second. So the velocity is now 0 from 4 to 7 seconds. So this graph is going to very abruptly just go and go to 0 until we get to 7 seconds. There's a question, the VT graph is the derivative of the XT graph. That is correct. This is not a calculus-based class, though, so I'm teaching this to you without calculus formulas. So you need to know that how to interpret this, but you don't need to know calculus to do that. Okay. And then from 7 to 9 seconds, we can see that the velocity was -5. So the graph is going to abruptly drop to -5, which is perhaps right here, like that. Okay, so that would be the velocity time graph representing that motion. Okay, so what is the meaning of slope of a velocity time graph? Okay, well, that would be change in the vertical variable, which is velocity, divided by change in the horizontal variable, which is time. Change in velocity over change in time. So the slope is equal to the acceleration. So acceleration is slope of a velocity time graph. So this is our third nugget of information for today. One of the things you have to be really careful about is you have to know what kind of graph you are looking at. I beg you, please look at the axes of your graph and read them. Read the axes of your graph, okay? Because you can get really confused. If you're looking at this graph right here, okay, and I say, what is the meaning of slope? Well, that's a position time graph. So the meaning of slope is velocity, okay? But what if you're looking at a velocity time graph? The meaning of slope is acceleration. So the meaning completely changes. The meaning of slope completely changes depending on what graph you are looking at, all right? So you will get totally confused if you don't read the axes, all right? Let me give you a good example. What would this position time graph mean? If your position time graph is sitting at a constant value of position like that, this would mean you are at rest. Okay? Because the position value is not changing. The slope of this is 0. But what if you had a velocity time graph that looked exactly the same? Like that. So if you weren't looking at the axes, this graph looks the same as that graph, right? They're both just a flat line, okay? But this one does not represent being at rest because look it, you have a velocity that is staying constant at some steady value. So this is moving in the positive direction at a constant velocity. Okay? So the meaning of that is completely different. Here you're not moving, here you are moving, but the graphs look the same. Okay? So I cannot emphasize enough the importance of reading the axes of a graph. And the further you go in science, I would say the more important that becomes because you get more and more complicated graphs. Okay? If you have a velocity time graph, what does that mean if the velocity is positive? That means that you are moving in the positive direction. So you're moving forward. So anytime the velocity is up here, that means you're moving forward. What does it mean if you have a negative velocity? That means you're moving back. Okay? And if your velocity is 0, you are at rest. Okay? So what if I had a velocity time graph that looks like this? Okay? So I'm going to break this up into 4 segments. Okay? The first segment is segment 1. The second segment is segment 2. Okay. The third segment, it's not really a segment, it's just a single point, segment 3. And then the fourth segment is this part right here where it goes negative. Okay? So what is happening in segment, I'm going to write this along the bottom here. I'm trying to only use one piece of paper. For segment 1, the velocity is positive, okay, so you're moving forward, but the velocity is not changing, okay? So in segment 1, you are moving forward with a constant velocity, okay? What's happening in segment 2? All right, what's happening in segment 2? Well, you can see that your velocity is still positive. It's still above the time axis, right? It's still positive, but the velocity is approaching 0. Okay, see how it's getting close to the horizontal axis. So in this case, you are moving forward because the velocity is positive, but your speed is approaching 0. So you're moving forward, but you are slowing down. Okay. What's happening at segment 3? Segment 3, your velocity is 0. So you're at rest. Just for a moment, though. Just for a brief moment. Okay, so I'll say at rest momentarily. And I'm going to wait for you guys to type into the live chat what is happening in segment 4. So I'm going to wait for about 20 seconds for someone to type into the live chat what's happening in segment 4. I'll do this. So, okay, so it's moving in the negative direction. Very good. So the velocity is negative now, so it's moving back. Okay. However, it is not moving at a constant velocity back because look we can see that here the velocity is 0. Here the velocity is maybe -1. Here the velocity is -2. Here the velocity is -3. So what's happening to the magnitude of that velocity is the magnitude is getting larger. Okay? So this is moving backwards, but speeding up. Okay? So that is the interpretation of that. So notice how the interpretation is completely different from a position time graph. All right? So that is my lesson for today. So what we are going to do is we are going to transition over to the Zoom room, and I will meet you there in about 1 minute. Okay? Bye-bye.